Hi, welcome back to our calculus videos. On this one, we're going to talk about linear approximations and differentials. So a linear approximation is just a tangent line to a function. So for example, if I have this function, which is the square root of x plus 3, this is f of x equals root x plus 3. So you know this is a shift left 3 because h is always the opposite of what you think it is. And if I wanted a linear approximation, what I can do is I can take a linear approximation and I've got some boundary points. So maybe my linear approximation looks something like that. Or maybe my linear approximation is right here. It's a tangent line to the curve. So I've got these tangent lines everywhere. And I'm going to try to use these tangent lines to approximate the derivative at some points. So let me delete that. Nope, that's not what I wanted. There we go. And I want to find the linearization at a equals 1. So I'm finding a tangent line at a equals 1. Our linearization formula is right here. So I've got to find out what's the tangent line to the curve at some point A. Well, in our case, we're looking for the tangent line at a equals 1. So what I'm trying to find is, if I go to 1 right here, I'm trying to find the tangent line to that curve that's just barely going to touch it at x or a equals 1. I mean, you could think of this as a lot like f of x plus f prime of x, maybe we'll call it x1 or x naught, times x minus x1 or x naught. So here's our function. I've got my a equals 1. And what I need to do is I need to start off with f of a. So if my linearization L of x equals f of a plus f prime of a times x minus a, the only things that I'm changing are, I'll plug in a number, plug in a number, plug in a number there. This x is going to stay the same. So let's see what we get. F of a, this is a equals 1. A equals 1. So let's start with f of x. F of x is root x plus 3. So f of a, in this case f of 1, is the square root of 1 plus 3, which is 2. So this part is 2. Now I've got to figure out what's f prime of a. So I need to take the derivative of this function, square root of x plus 3. F prime of a is 1 over 2 root x plus 3 times the derivative of the stuff inside there. If we chain rule it, it's times 1. So if I take the derivative of the square root of x plus 3, then I get that thing. If I want f prime of a, that means I want f prime of 1, which is 1 over 2 times root 1 plus 3, which is 1/4. So let me erase some of this. So if I take my derivative and plug in a 1, I'm going to get that function, which is 1/4. And now that I've got my function at 1 and my derivative at 1, then all I've got to do is put it into the formula. So our linearization is f of 1 plus f prime of 1 times x minus 1. or in our case, we get the linearization. If I plug in f of 1 we found earlier was 2. So that's 2 plus 1/4 x minus 1. And if I simplify this function, I'm going to get our linearization function is going to be 1/4 x plus, not 2, but sorry, 1.75, or 1 3/4. So if we do the, distribute 1/4 x minus 1/4, 2 minus 1/4, it's 1 3/4. So our function is 1/4 x plus 1.75. And we can check that. I'm going to go to Desmos. There we go. Go to Desmos. Here's our function. Our function was 0.25x plus 1.75. Check it out. There's our linearization. There's our tangent line. And it looks like it touches at the point 1, 2. So our function is tangent at the point 1, 2. This is our linearization. The next part the question asks us is, are these approximations overestimates or underestimates? So what it's looking for there is it's saying, okay, if I want to approximate 3.98 and 4.05, then what it's saying is take root 3.98 is approximately, let me use my calculator, square root of 3.98. It's a little bit less than 2, of course, but it's 1.995. Square root of 4.05 is going to be a little bit more than 2. That's going to be 2.0125. So it's a pretty good approximation. But if I wanted to find an approximation using my my linearization, then if I were to zoom in here, you're going to see that this linearization, this tangent line in blue, is going to be an overestimate for both. Because my blue line is always going to be above that curve. It's above the curve on the left. It's above the curve on the right. But my function, because it's always below my tangent, below my linearization function, this function right here in blue is 1/4 x plus 1.75. I can see that my blue is always going to be an overestimate. It's always too high above the curve. And if I were to, plug in these values into my function, 1/4 x plus 1.75, we'll see that we end up with overestimates. Whatever I would get by plugging these numbers into the function would be higher than their true values. All right. So for what x values is the linear approximation accurate within 0.5 or accurate within 0.1? So what we're looking for there is, I want to know when is the difference between root x plus 3 and 1/4 x plus 1.75. When is that difference? That looks terrible. When is their difference going to be within 0.5? Or when is their difference going to be within 0.1? So I could set up this equation, or this inequality rather, to solve for my function. So what I got to do here, it's just saying when is the difference less than 0.5, when is the difference less than 0.1. I'll show you how to do this one, and then I'll give some examples here. So in this case, it's got to be negative 0.5 less than root x plus 3 minus 1/4 x minus 1.75 less than or equal to 0.5. And then if I add 1.75, I get 1.25 root x plus 3 minus 1/4 x 2.25. So I got to figure out when is this function going to be within 2.25 and 1.25 to 2.25. So I could try to find this by graphing this and using like a graphing calculator and a Desmos, or I could just do it algebraically, but here's the root of the function there. That's really what the question is asking us, is when is it accurate within this margin of error or that margin of error. Set the absolute value, the difference between them, less than that margin or equal to that margin. Set up your two-sided inequality, and then simplify, find your boundaries. All right, so I want to look at a few examples here. Let's see if we can find our linearization of let's do the linearization of, for example, 1 x squared sine of x, sorry, x squared sine of 2x at let's say a equals pi. Why not? So I've got to do a couple things. First of all, I've got to find out what is our linearization function. It's f of a plus f prime of a times x minus a. There's our linearization function. And if I wanted to find the linearization at a specific a value, all I've got to do is just take my f of a. So this would be pi squared times sine of 2 pi. Well, I know that sine of 2 pi is 0. So that's just 0. Plus f prime of a. So, okay, I got to find my derivative now. So if that's f of x, f prime is going to be first times the derivative of the second. So it's x squared times 2 cosine 2x. First times the derivative of the second for that first part. And then I got to find second times the derivative of the first. So I got to add, sorry, let me move this down here. Now I got to add on sine of 2x times 2x. And again, note that this part comes from the chain rule. You got to chain rule that sine. So what do I have here? I could simplify this as f prime equals 2x, x cosine 2x plus sine of 2x. So my f of a was 0. My f prime of, let's say, what was it, pi? My f prime of a is going to be 2 pi times pi times cosine of 2 pi plus sine of 2 pi. Okay, sine of 2 pi. Sine of 2 pi we know is 0. So I don't have to worry about that. And then cosine of 2 pi, well, I know cosine starts at 1, so cosine of 2 pi should be 1. So this is going to be 2 pi times 1, which is just 2 pi squared. So I get 2 pi squared x minus pi. The only things we plug in for our linearization, we plug in for f of a, we plug in our a value into the f prime equation, and we plug this in. We leave this x alone. And then we can distribute to both parts, and I get my linearization function is going to equal, this is 0, because sine of 2 pi is 0. So I get, what is that, 2 pi squared x, 2 pi squared x minus 2 pi cubed. So that's my linearization function. So my final answer would be linearization of x equals 2 pi squared x minus 2 pi cubed. So there's my linearization function. Let's do one more example. Let's go with, let me find a good one here. We're going to go with the linearization. Let's go with f of x equals x to the 4th plus 3x squared at a equals negative 2. So my linearization is f of a plus f prime of a times x minus a. And the things we plug in for are here, here, and here. All right, well, if that's my linearization, I better find my f prime. F prime, see if you can find your f prime and then plug it in and then unpause the video when you're done. So pause it, try it, unpause, check your work. This would be 4x cubed plus 6x. So f prime of a is f prime of negative 2 is negative 32, because it's negative 8 times 4, minus 12 is negative 44. So my linearization function is going to be f of a. If I plug in an a here, let me do that. F of a is f of negative 2 is, that's 16 plus 3 times 4 plus 12 is 28. 16 plus 12 is 28. All right, so my linearization then is going to be my f of a, which is 28, plus my f prime of a, which is a negative 44, times x minus a. Let's simplify this. I get 28 minus 44x minus 88. So my linearization, my tangent function, is going to be negative 44x minus 60. So that's the equation of the tangent line to that function, f of x equals x to the 4th plus 3x squared at the point a equals negative 2. Which makes sense. If you were to graph that x to the 4th plus 3x squared, let's get rid of that. X to the 4th plus 3x squared. You go to negative 2. I mean, at negative 2, you're already pretty steep here. So negative 2, I'm not even at negative 2. There, I'm getting to negative 2, almost there. There's negative 2, that's pretty steep. All right, check out the differentials video coming soon too.